So far we understood that turbulent flow in turbomachinery is one level ahead of uh, regular turbulent flow. In this figure, actually, you you are seeing most of the unsteady and turbulent phenomena in axial turbomachinery, according to whether if they are periodic or if they are not periodic or aperiodic. As you can see, you have the unsteady, the total unsteadiness inside the turbo machine, and you can classify it as, let's say, uh, time periodic phenomena unsteadiness in here. This is time periodic. And there is this side, which is only the chaotic and aperiodic phenomena. So first of all, let's look at the right part. The right part suggests that you could have some kind of aperiodic, chaotic phenomena, like the inflow turbulence. So inflow turbulence is not a rotating, right? Inflow, they're just the incoming flow is not rotating, so it has a chaotic and aperiodic turbulence. The end wall boundaries, the boundaries will not rotate, right? The wall is not rotating. That's why there is no, let's say, just a second. There is no, no, I cannot. Yeah, there is no rotation on the wall, and also the wake shear layers. The shear layers are not rotating, and also you have some vortices which are anisotropic vortices, and they are kind of get their position in the aperiodic turbulence. But in the unsteady, let's say, phenomena, you actually there is this paper, and you can refer to this paper to see this also figure in there. So in this paper, they tried to just categorize this unsteadiness in the turbomachinery as forced and unforced unsteadiness. So they kind of they were able to categorize this unsteadiness into two parts, but they said that there will be uh, the interaction between some of these forced unsteadiness and unforced unsteadiness. So sometimes they could see some of the effects from forced unsteadiness inside unforced unsteadinesses, and they cannot make a very they cannot give a very bright distinction for each part. But the thing is, your unforced unsteadinesses and your turbulence part are the non-deterministic parts. Just as I said, when you have your turbulence as u is equal to u prime plus u bar plus u prime, this u prime is something that you cannot determine it. It's a fluctuation, right? Something is fluctuating, and if it is fluctuating, you cannot determine how it is fluctuating. You just measure this, and then you see that okay, they are fluctuating around this mean value, and okay, at any point of time you can see what is the fluctuation, but you cannot determine this fluctuation. That's why it is inside a non-deterministic part of this chart. But the deterministic parts, as you can see in here, are, for example, the interactions between rotor and stator and the passage flow structures. So the leakage flow from the tip, the secondary flows, you're remembering that we mentioned the tip leakage, the secondary flows, the wake mixings in the turbomachinery. I already gave you some pictures of those. And also you have the interaction between rotor and stator. So one rotor and one stator, there is the interaction from the flow coming passing from the rotor and hitting the stator. So these are all interactions. But because of the, let's say, uh, physics of turbo machine, the rotor is rotating. So it's rotating with some kind of RPM. This RPM shows you the frequency, shows you the period, shows you everything of this. That's why these are deterministic. They have certain values. Okay? This is another study in UK, and in UK they were able to kind of uh, use some modeling with time average of unsteady motion, and then the solution of the time averaged flow equations with deterministic stresses. Again, I put the reference in here. You can go to that paper and read this paper as well. But it's let's say they were able to determine the uh, actually distinguish between the unsteady solution and the time average of let's say the steady unsteady solution, and then time averaged of unsteady and time averaged flow equation. So there will be some distinguished parts between these two. Okay, what we said so far. So far we said we have Navier-Stokes equations. Where is my mouse? We have Navier-Stokes equations. And we said that these Navier-Stokes equations are giving, let's say, are governing instantaneous variables like u and t. These are instantaneous. And if somebody can solve these Navier-Stokes equations, actually he is doing DNS, or direct numerical simulation. Direct means you are getting the solution, instantaneous solution, directly. So Navier-Stokes equations, when you average these Navier-Stokes equations, we said that when you, let's say, average this, when you average Navier-Stokes, you are getting Rand's equations. What are Rand's equations? Reynolds average Navier-Stokes. These are Rand's. Reynolds average means that you are using Reynolds decomposition to put inside the Navier-Stokes equations and come up with only the averaged values. See, these are only averaged values. And the terms that I was talking about, the additional terms in Rand's, are these terms. See, two fluctuations multiplied and then get averaged. This is nothing that you can infer from the flow itself, because you're dealing with mean flow. You're dealing with u bar, but in here you're having u prime times u prime bar. These two primes means fluctuations. Fluctuations are not they do not exist in your mean flow, right? That's why you have to model these fluctuations with some modeling approaches, and these modeling approaches actually make your CFD models, like algebraic models, K epsilon models, K omega models, all of those things. But the story does not end for turbomachinery. For turbomachinery, we said that we also have unsteadiness in turbomachines. We have RPM, the turbomachine is rotating. That's why you have to include unsteadiness in turbomachines. This means that you will end up with U-Rans equations, which means unsteady Rans equations. And as you see, you're dealing with tilde uh, values. So these tilde values, the governing, the Urans equations is the governing equation for tilde values. That means that there is no steady condition in turbomachinery. Let me clean this. These parts of Euron's equations are important for us. For example, this term in here, you're seeing that two double prime values are multiplied and then get averaged. If you remember, double primes were deterministic fluctuations, right? That's why from now on, when two values are, um, let's say, multiplied, we call them stresses. Just as in the case of rents, we call these as Reynolds stresses. Okay, Reynolds stresses. In here, in turbomachinery, you have double primes multiplied. We call them uh, deterministic stresses. Deterministic stresses. What is this part? This part has a special name. This part has a special name which we call it average passage. Average passage turbulent stress. Turbulent stress. Average passage because it has this bar and then tilde. So this is average passage stress. Stress why? Because these are two components of fluctuations that are multiplied. That's why we call it as stress. And then so we have deterministic stress and we have average passage stress. Now, if I want to show you this average passage stress, what was it look like? We said that this average passage stress is U prime I, U prime J, bar, tilde, right? Or not tilde in here, it's, if you want to show this U prime I, U prime J, what does it look like? It is in the matrix form because it's a tensor. So this is the U prime 1, U prime 1 bar, U prime 1, U prime 2 bar, U prime 1, U prime 3 bar, U prime 2, U prime 1 bar, U prime 2, U prime 2 bar, U prime 2, U prime 3 bar, U prime 3, U prime 1, and this is 3, 2, and this is 3, 3. So this is a stress. You know from, you remember from your uh, courses related to the structure, like what was the name of the course? Um Strength of materials. You remember these tensors, right? From there. These are the same things. So it has a 3 by 3, it is 9, it has a 9, uh, let's say, arrays inside. So each one is a tensor. These are normals. On the diagonal, you're dealing with normal uh, shear stresses or in the non-diagonal shapes. So these are the normal stresses. These are the triangles of the shear stresses. You remember from strengths of materials that they were kind of symmetric. So 3 1 is 1 equal to 1 3, 2 1 is 1 2, and 3 2 is equal to 3 2. So in here, there is this thing. If you sum up these diagonal arrays, these diagonal components, you will actually get your turbulent kinetic energy. So when we are talking about turbulent kinetic energy, it means that From physics, kinetic energy, you remember, was 1 over 2 mv squared, right? Just remember this. Turbulent kinetic energy is the kinetic energy of these fluctuations, okay? So 1 over 2 of fluctuations. So fluctuations, we have ui bar. Again, because we have, just remember what I said, when you have uh, two i's in here, it means that you have to sum up. So it means that it is 1 over 2, u1, u1, it is u, right? These are primes, u1, u1, it is u, and then plus u2, u2, which is v, u3, u3, which is w. So turbulent kinetic energy is actually the sum up all the fluctuations in u, v, and w. In turbomachinery, there is deterministic kinetic energy as well as turbulent kinetic energy, and we call it as K deterministic. Is deterministic kinetic energy. K deterministic is 1 over 2 of what we said deterministic stresses in the previous slide. So ui double prime bar. These two, K and K deterministic, are good measures to compare the magnitude of U prime and also U double prime. U prime is your turbulent fluctuation. It is turbulent fluctuation. U double prime is deterministic fluctuation. So please keep these stuff in mind. These are important for us. Now the story is kind of much more complex. We said we have Navier-Stokes, and these Navier-Stokes equations are equations to solve for instantaneous velocity. We said when we do some modeling in CFD, we are getting the shape, the behavior of averaged flow. How? Just by using Rand's equations, Reynolds average Navier-Stokes. We said if we want to model turbomachinery, we have to include unsteadiness, and we use Uran's equations. And Uran's equation actually gives me the behavior of U tilde, not even U bar, U tilde. Also, there is another step in here, which we call it apparence. And apparence also gives us U tilde, and apparence is actually averaged passage, Reynolds average Navier-Stokes equation. This apparence approach actually accounts for the effect of the phase-dependent unsteadiness. Phase-dependent, remember that I said there is a blade and it is rotating, it comes to this. So this is actually called the phase of the blade. Why? Because from the horizontal it has, for example, alpha decrease. This is called the phase of this blade. So this apparence or averaged passage is actually accounts for the effect of this phase dependent unsteadiness and also special uh, non-uniformities associated with neighboring blade flow. But apparence does not resolve the, let's say, two neighboring blade rows effects. Um, There is a paper from my PhD supervisor, Professor Uzol. Um, he wrote this paper back in 2002. I strongly advise you to go over this paper as well. some part of this paper says that uh, you have three different averaging operators that are being employed. The first is the ensemble averaging that accounts for the turbulence and is used in unsteady runs, in U runs. The second is time averaging that removes the deterministic unsteady flow, covering time scales that are of the order of the shaft period, including the phase-dependent variation in flow structure. And the third operator is passage-to-passage averaging. And this passage-to-passage averaging is necessary for turbomachinery with varying number of rotors and stators on consecutive stages. So, for example, in the first stage, you have, for example, uh, 10 rotors, and then after 10 rotor blades, you have 8 stator blades, and then in the second stage, the number of rotors and stators will be very different. This makes some difficulties. That's why we are using passage-to-passage averaging here. So we are saying that when the flow is leaving one passage, we are average the whole thing in that passage, and we are giving this average to the consecutive passage or consecutive stage. When these three different operators, as I said, one operator was a spatial average. A spatial means in a space, in a space. And then we have time average. When you are doing in a space, it means that you are doing ensemble averaging. For time, we are taking time averaging, and then we said that we have passage to passage, P to P, and this is passage to passage averaging. When you apply all these operators on the Navier-Stokes equations, you will get Apran's equations. Where is my pen? So Apran's equations actually came from application of three different averaging on the Navier-Stokes, let's say, equations. What else can I tell you? Yeah, so this is actually the equation for the Aprans and also the Urans equations. And in this equation, as we said, this was deterministic stress. This was average passage stress. So in this in deterministic stress, you need to model this. So here you have to model this. Modeling is required. Right now, we are not talking about measuring in turbomachinery. We are kind of digging the equations, and we see that if we need to model these, what should be modeled actually in these equations. So for the deterministic stresses, you need to model. This is very clear because you already had to model this in normal turbulence flow. So this is turbulence modeling. This is turbulence modeling. This is turbulence modeling. So see, if you have a, let's say, simple turbulence modeling, you don't have this deterministic stress modeling, right? So turbulence modeling is actually easier to do. But if you have a turbomachinery problem, you have to do two modelings. One for the deterministic stresses, one for the turbulence stresses. So that's why right now you're saying keşke bu dersi almasaydım. Because you're having double difficulties in here. Why I am talking about these modelings? In modelings, you have to model these terms with some physically meaning thing, right? Where do you get this physics actually? You get this physics from experimental data. So unless you have an experimental data, you cannot model these two in turbomachinery. That's why in turbomachinery, even nowadays, we are searching for better and better modelings. We are searching from these modelings from experimental data. And nowadays, with this much of data that we have in hand, it's a good practice to actually create new models based on artificial intelligence as well. Because we have too many approaches in artificial intelligence to get some new models out of big data that we have out there. So this could be a motivation for the guys who are doing the uh, masters or PhDs to do their thesis or studies about the turbomachinery modelings using artificial intelligence, deep learning, and machine learning stuff. So we said that if these modelings are not 100% true, you may have some values of, for example, U tilde that is going up or down from its exact value. That's why we said that we need good experimental data to check the accuracy of these modelings that we are introducing. For example, for turbulence modeling, you already know that you have kind of models like K epsilon and K omega models. Okay, in these K epsilon and K omega models, if you go to ANSYS or whatever, you have some tuning parameters there. These tuning parameters are actually those parameters that you are inferring from experimental data. So you do some experiments and they give you some tuning parameters, and then you put these tuning parameters into K epsilon or K omega models to get results better and better.